Okay. So today I will solve 2023 mathematics gate question from linear algebra, question number 22 and question number 34. I will play the videos. First question number 22. So if you have any doubt, you can ask question. Okay, can you see the video? Okay, so let's start.
Okay, so today we will solve Gate 2023 mathematics question from linear algebra. This is question number 22. This is 1 mark question. So what is this question saying? Let T from R4 to R4. So this is a linear transformation, and the null space of T is the which is the subspace of R4, which is given by this, right? And saying that if the rank of T minus 3i, which is 3, where I is the identity map on R4, then we have to find the minimal polynomial of T. So 4 options are given. Option number A is the minimal polynomial will be x into x minus 3. Option B is minimal polynomial will be x into x minus 3 whole cube. Option number C is minimal polynomial is x cube into x minus 3. And option number D is x square into x minus 3 whole square. Okay. So let's solve this one. Also, in order to solving the question, you can look at for NPTEL reference. This is the NPTEL reference. Okay. So let's solve. So whatever definition and results needed in solving the question, I will write it whenever it will need. Okay. So what is null space of T is given by this. So let me denote this as null space of T. Let this is called null space of T. What is this? This is by definition basically all such vector in V such that TV equals to 0, right? So what it is given, null space of T, here it is given that this is a subset of R4 such that 4x1 plus 3x2 plus 2x3 plus x4 equals to 0. Okay. So let's find what will be the null space. So this equation is given 4x1 plus 3x2 plus 2x3 plus x4 equals to 0. So from here we can write x4 in terms of this, right? 4 minus x1 minus 3x2 minus 2x3. So as it is only one equation is given, so we can write x4 in terms of x1, x2, x3. So then we can write this, then null space of T. We can put it here, right? x1, x2, x3. In x4 you can write in this minus 4x1 minus 3x2 minus 2x3, where x1, x2, x3 are x1, x2, x3. These are real numbers. So then what it will look like? So you can write x1, you can take common 1, 0, 0 minus 4 plus x2 0, 1, 0 minus 3 plus x3 0, 0, 1 minus 2, right? And while this is our value x1, x2, x3 are real number, right? So here you can check that this, let me call this is v1. What is v1? 1 0 0 minus 4. v2 0 1 0 minus 3. v3 0 0 1 minus 2. So one can easily check that these three vectors are linearly independent. So these are v1, v2, because you can always check that in the first component only v1 is non-zero, or in the second component v2 is only one non-zero, and the third component v3 is 1. So one can easily check that these are linearly independent. And there belongs to the null space of T, right? Because null space T is basically the linear combination of these three vectors. So they will generate this null space. So null space of T is basically the span of these three. Span V1, V2, V3. Right. So null space has dimension also 3. What is meaning by these are in the null space? So by definition, this is the meaning that Tv1 is 0, right? Tv2 is also 0. Tv3 is also 0. Right. So from there you can easily see that Tv1, you can write 0 into v1. Tv2, you can write it 0 into v2, and Tv3, you can write it 0 into v3. And v1, v2, v3 are linearly independent, so they are non-zero vectors, right? So these three equations are telling that v1, v2, v3 are the eigenvector, right? Eigenvector of T with eigenvalue 0, right? Why? Let me give the definition. If someone has any doubt, let me write the definition. So definition, what is a vector, a non-zero vector V, so this is in the vector space V, is called an eigenvector of the linear operator or transformation. Linear operator T with eigenvalue lambda if Tv equals to lambda, right? It will satisfy. V is in the space B. So this you can also write, this is same as, right, T, you can take it this side, minus lambda V is 0, right? This is same as this. And so what is meaning by this one? So here it is basically the identity operator is there. So let me write it explicitly. Means lambda into identity V is 0. Right. So it is the where V is non-zero. So lambda is called an eigenvalue with eigenvector V if it is satisfies this equation. Right. So which is same as saying that T minus lambda is not invertible. Right, because V is in the null space of T minus lambda, so it is not 1 1. So a non-zero vector which sends T minus lambda into 0 vector, which is the meaning that T minus lambda is not invertible. Right? So this is the definition. So what we have got, that V1, V2, V3 are the eigenvectors of T with eigenvalue 0. Okay. So from this one we have got the this one, and now we use this one, right? Rank of t minus 3i equals to 3. So let's see what we have got from there.
Okay, up to this point, any doubt? No? Okay, let's continue then.
Rank of t minus 3 identity 3i is 3, right? So what is this saying? So t is a linear transformation from R4 to this satisfies the eigenvalue G. See what we have got from there. Rank of t minus 3 identity 3i is 3, right? So what is this saying? So t is a linear transformation from R4 to R4, right? And identity is also a linear transformation from R4 to R4. So t minus 3i it is also a linear transformation from R4 to R4. So rank of 3 is given. So rank of t minus 3i. So this is same as the dimension of the range space, right? Dimension of the range space. Range space of t minus 3i. So this is the definition of the rank, right? Dimension of the range space of t minus 3. And so this is 3, but t minus 3i is a map from R4 to R4, and it has dimension of the range space is 3, so which is strictly less than 4, right? Because dimension of R4 is 4, so which implies t minus 3i is not onto, right? Because its range has dimension 3, but it is a map from R4 to R4, which has a dimension 4, and it has in range space of t minus 3 has a dimension 3. So this is not on, and as this is finite dimensional map from R4 to R4, this is a bounded linear operator, which implies t minus 3i is not invertible, right? Because it is not onto means not bijective, so it is not invertible. So what we have seen earlier, that if t minus lambda is not invertible, it's saying that lambda is an eigenvalue of t, right? So which implies that from that result, so what we have discussed about, from there we get 3 is an eigenvalue of t. So 3 is So we get, so earlier we have got 0 is an eigenvalue of t. Now we have got 3 is also an eigenvalue of t. Right. So let V4 be the corresponding eigenvector. Let V4 be the corresponding eigenvector of t. Eigenvector of t means what is saying that t V4 equals to 3V, right? And so for corresponding to 0 we got 3 eigenvector, right? Corresponding to 0 we get V1, V2, V3, these 3 eigenvector. And corresponding to V4 we have get this eigenvector V4, right? Because 3 is an eigenvalue, so it has an eigenvector, we have called it V4. And so as there is let me record one also result also. So suppose if t is a linear operator, if t is a linear operator, so eigenvectors corresponding to two different eigenvalues are always independent. So what this the result is saying? Suppose let V1 be an eigenvector, let's say W1. T W1 equals to some lambda 1 W1 and T W2 equals to lambda 2 W2. And if lambda 1 not equals to lambda 2, then this result is saying that W1 and W2 are linearly independent. Right. So we'll use this. So for 0 we have got, what we have got? These 3 eigenvectors, V1, V2 and V3. And corresponding to 3 we have got eigenvector V4. So as 0 and 3 are different, so V4 is linearly independent to all the 3. So therefore, using the above result, you can see we have that V4 is linearly independent to this V1, V2 and V3, all of 3 vectors, right? So we have, therefore we have got 4 linearly independent vectors. So we get V1, V2, V3, V4. This set is linearly independent. And note also that all 4 are eigenvector of T. Note also that these 4 vectors are eigenvectors of T. and as T is a map from R4 to R4, and you have got these 4 are eigenvectors, and so this has, so they are the basis of R4, right? So you have got a basis of R4 which are the means the, we have got a basis of R4 which are consist of eigenvectors of T. So from here we can use a one result that the operator T is diagonalizable. Now let me have one result. T, which is a T is a linear operator. On T, then T is diagonalizable if and only so not if there is if there is a basis of G for which each vectors of these are vector G, each of them of which is an eigenvector. Right. So what this is saying, that T is called diagonalizable if we can find a basis for the vector space B which are consist of the eigenvectors of T. And what we have got, this is saying exactly the same thing, right? We have got a basis for R4 which are consist of the eigenvectors of T. So therefore our T is diagonalizable. So therefore T is diagonalizable. Right. So we've got that our linear operator is diagonalizable. So what we have to find? We have to find the minimal polynomial, right? So here we can also use one more result that if a linear operator is diagonalizable, so result. So T is diagonalizable if and only the minimal polynomial of T has the form P of some x, it will look like x minus c1 x minus ck. So means the minimal polynomial factors into linear factor, right, where c1 up to ck are distinct elements on the field, or the vector space is over field of some field, right? Distinct elements of field, where B is the vector space of array. So it's saying that T is diagonalizable if and only if the corresponding minimal polynomial will be factor into linear factors. So what we have got, right? So we will use this theorem. So as T has two eigenvalue, eigenvalue 0 and 3 with corresponding eigenvectors are v1, v2, v3 and v4 respectively. Right. So how the minimal polynomial look like, right? So it can, so the minimal polynomial, therefore, so what will be the characteristic polynomial? So then the characteristic polynomial will be, so the minimal polynomial will be the linear factor, right? And it has two different eigenvalues, so 0 and 3. So therefore the minimal polynomial will be x into x minus 3, right?
Yes. T now either B or C. No, let me complete it, then I will answer it.
So let P of x equals to x minus 0 corresponding to eigenvalue 0 and x minus 3, because it cannot have more power, right? Because it will be linear factors. So therefore minimal polynomial will be x into x minus 3. So you have got the minimal polynomial for the linear transform of T is x into x minus 3. So therefore which option is correct? Option number A is correct. Okay.
Okay, now tell me what is the doubt? Did you get? Yes. Okay, so because that T is diagonalizable, so minimal polynomial will be linear factors, and because 0 and 3 are the only eigenvalues, so only x into x minus 3 will be the only option. And characteristic polynomial will be x cube into x minus 3. Yeah, any other doubt? Okay, others? Oh, okay. So, yeah, means when suppose the space, so whenever it will be diagonalizable, suppose, so then the minimal polynomial should not be any repetition, right? Only the linear factor should be there. So it might be the case that minimal polynomial you have to check always. Means in that case, if it is not diagonalizable, so in that case sometimes it may happen that minimal polynomial should look like x square into x minus 3. It might be x cube into x minus 3. You cannot always say how the minimal polynomial. You have to check, put the linear transformation, means compute the matrix and put in that form t cube into t minus 3i. You have to check that time, right? First, means minimal polynomial is not straightforward to compute. You have to always just, means you cannot tell it that what is the minimal polynomial. You have to test it by putting the matrix of the linear transformation. But in diagonalizable case, this is easier, that you can always tell that if it is diagonalizable, it should be linear factors. Okay, any other question? Okay, so let's move to the next question. Question number, okay.
Okay, so today we will solve Gate 2023 mathematics question from linear algebra. So this is a question number 34. So this is 1 mark question. What this is saying, consider R4 with inner product. So xy is the inner product, is defined xi yi, I summation run from I equals to 1 to 4, where x is this vector in R4 and y is this vector in R4. And what is M? M is a subspace which is given this, and M part, this is called the orthogonal complement of it. Then you have to find the dimension of the M part. It will be what? Okay. So let's see. So this is the NPTEL reference in order to solve this problem. Okay, let's start. So what is, so inner product space, let me, so this is the on R4, right? On R4 we have two vector x, which is x1, x2, x3, x4, and y is another vector y1, y2, y3, y4. So an inner product, so this is a map from V cross V to R4 cross R4 to R. So how this is defined? So this is basically a map from R4 cross R4 to R. How this is defined? Xy is have just the sum I equals to 1 to 4 xi y1. So basically x1 y1 plus x2 y2 plus x3 y3 plus x4 y4. So there are some property that this is symmetric in both variable, this is linear in both variable. Okay, and this is positive definite, means if vector is non-zero, then V is non-zero, then inner product V is stated positive. So you can check that all this property will be satisfied for this inner product. So this is standard. So this is the inner product on R4. Okay, and what is given that M is a subspace of R4, it is given that x1 equals to x3. So this is subspace given x1, x2, x3, x4 belongs to R4 such that x1 equals to x3. Right? You can easily check that this is a subspace for subspace of R4. So let's find what will be the dimension of M. Right. So as x1 equals to x3, let's put it there, x1, x2, x1 and x4, right? Where this x1, x2 and x4 all are real numbers. So this you can then write x1 1 0 1 0 plus x2 0 1 0 0 plus x4 0 0 0 1, right? So let's call this is v1 to sorry 1 0 1 0, v2 let me calling it 0 1 0 0 and v3 0 0 0 1. And this is easy to check that all v1 v2 v3 all three are linearly independent. No, v1 v2 v3 are linearly independent. So M is basically therefore a span of these three vectors, right? And these are linearly independent. So as M is basically span of means finite linear combination of these three, right? V1, V2, V3. So which implies dimension of M is 3, right? So we have to find out the dimension of M, which is 3. We have to find the dimension of the orthogonal complement. So what is orthogonal complement? How it is defined? So let me write down orthogonal complement. So this is defined, this is a concept on inner product space only, right? So let V be an inner product space. And let for any set we can define orthogonal complement. For any set S, the orthogonal complement of S. This is the definition. Orthogonal complement of S denoted by, this is denoted by S part by this notation, which is so S part this contain all x in this space B such that x inner product y is 0 or all y in S. So this is called the orthogonal complement. One can easily check that this S part is always a vector subspace of V, whether S is a subspace of V or not, right? So this is one important observation of this S part. So here we have to find the dimension of M part. So okay, so this is okay. So M part, similarly M is this subspace, so M part will be like this. M part will be all such x in R4 such that x inner product y is 0 for all y in M, right? So we have to find the dimension of this subspace M par, because this is automatically a subspace. What we have said, that M par will always be a subspace of the vector space. So this is a subspace of R4. Now let us write down another result. So it is saying if W be a subspace open in our product space, so this is finite dimensional, right? Finite dimension. W be finite dimensional subspace open in our product space. V, then we can write V equals to W direct sum W path, right? And so direct sum means this is saying that W intersection W path as single, and this is, and dimension of V is dimension of W plus dimension of W path, right? W be a finite dimensional subspace of an inner product space B, then B can be written as W direct sum W part, and dimension of B will be dimension of W plus dimension of W part. Okay, we will use this result to prove our that dimension of what will be the dimension of M part, right? So therefore what will be the dimension of M par? So therefore dimension of M par will be dimension of what is V here. So as M is a subspace of R4, so dimension of R4 minus dimension of M. So dimension of R4 is 4, and dimension of M3 we have found out that this is 3. So dimension of M is 3, so we have got dimension of M part is 1. Therefore dimension of M part is equals to, this is 1. Okay.
So okay, any doubt with this? So we have found out the dimension of the M part. Can you tell me, so we have got the dimension of M part is 1, right? So what is that subspace? Can anyone tell me? Means how the subspace, what are the elements, means can you give one a vector in M part? M was given to be the, we got 3 vectors, right, in M, 1 0 1 0, 0 1 0 0 0 0 0 1. Yeah, so empire will be generated by 1 0 minus 1 0. Okay, so let me tell how. Yeah, you are right. So what we have got, m, this is the span of what we have got, 1 0 1 0, and other vectors 0 1 0 0 and 0 0 0 1. So suppose let b equals to b1 b2 b3 and b4, which belongs to M parp. So then by the definition, B inner product any element y should be 0 for y in M, right? And because this is the span of these 3 elements, so just test it with these 3 elements. So first one, it will be, so B inner product with this one, 1 0 1 0. So from here what we will got? From here you will get B1 plus B3 is 0. Next one, if we apply B inner product with 0 1 0 0, from here you will get B2 equals to 0. The last one, B inner product 0 0 0 1 equals to 0. So from here you will get B4 equals to 0. So from the first one we can write it B3 equals to minus B1. So what we have got? So B will look like B1 0 minus B3 minus B1 and 0. So this is basically B1 times 1 0 minus 1 0. So this is the subspace, right? So M parp will look like span of this one. So that's why it is one dimensional. 1 0 minus 1 0. What you have said, it's correct. It's general. Yeah, what will happen in case of infinite dimension for M and M parp? Yeah, infinite dimension case, you cannot always say that direct sum, you can write it always M and M parp, right? For that you need some condition that it is a closed subspace, then M parp you can write is V in Hilbert space you can write, means not in anywhere, means you should have notion of their inner product. So Hilbert space you have to take, but there is notion of complement. So in that case, when B is, suppose W is a closed subspace, so in that case you can define the complement. You can write B equals to W direct sum W parp. But finite dimension you can always write. Did you get it? Okay, any other doubt? Yeah, Anjana, previous to question that why you have said the minimal and characteristic polynomial are the same. Suppose take this example, when the matrix have or linear transforms all the distinct eigenvalues and you have all means all the eigenvalues. Suppose it is over, it's mapped from Rn to Rn, it has n distinct eigenvalues. So corresponding n distinct eigenvalues, you will get n distinct eigenvectors, right? And so they will form a basis, so it is diagonalizable. So in that case it is diagonalizable and it has n distinct eigenvectors. So minimal polynomial and characteristic polynomial will be same, right? So in case of n different eigenvalues and if it is mapped from Rn to Rn, so in that case you can tell that minimal and characteristic polynomial are same. Yeah, and if it is same, then yeah, I think the converse is also true. If the minimal and characteristic polynomial are same, then the eigenspace corresponding to eigenvalue must be of dimension 1, otherwise it will not be whole. Yeah. So that For that case, you can easily check that minimal polynomial will be what. But when you have not enough eigenvalues, then in that case you have to check by putting the matrix in that polynomial, right? Okay, any other questions? Okay, no question. So next class we will solve some problem from measure theory. So this is the topic from real analysis. Okay. Tomorrow, yeah, session will be hold. It is not like that. It is holiday. The session will not hold. Yeah. If there is a live session, it will hold. Yeah, Anjan, I will upload these notes in my YouTube channel. In my YouTube channel, you will find it. In the description, I will add. I will upload this video also in the YouTube channel. On my YouTube channel, you can find it. Yeah, thank you. Okay, let me write the name. Yeah, just remember the name DWIP, otherwise you will not find it. Okay, let me stop sharing. Okay, bye then. If there is no other question, let's meet on the next week. Bye.